Hello, welcome everybody. Hey, thank you so much for joining us today. Um, Today's webinar is it's going to be unique. It's going to be fun. This is the last part of a 3 webinar series. Today's webinar we're going to be talking about certified fire and gas equipment, kind of how you certify a product, and then we'll go into actually the gas detection and the placement of gas detectors, and the importance of it. Now. The unique thing with today's webinar is usually exida. We always hold these webinars every week, but today we are honored. We have one of our colleague or our experts from Micropack, Mr. James McNay. He's joining us today on today's webinar, and we're going to introduce him shortly. But for right now, my name is Ted Stewart. I'm the Program Development and Compliance Manager here for exida. I have a little over 10 years of safety and high availability automation system experience. My previous occupations, I worked for Lockheed Martin in missiles and fire control out of Orlando, Florida, where I was a test engineer. I went over to Harris Corporation, working for wireless product groups. That's where I started getting into Lean Six Sigma. I got into new product introduction, and that's how my career started, where I loved program management. I loved troubleshooting and finding new solutions to things. I transferred over to exida, probably one of the best decisions I've ever made. Been with them for about 6 years now. I now manage the OEM certification division. I'm a deputy quality manager, and I'm also responsible for a lot of those standards that people tend to fall asleep to. But it's great because I get to help bring us into new industries, whether it's functional safety, cybersecurity, machinery, robotics, automotive. I mean, of course, today we're talking about fire and gas. But around all the work that we do, because we're a global company, you kind of work around the clock. I like to say that whenever I get time permitted, I thoroughly enjoy cycling. And my wife and I were huge into home renovation projects. We love flipping houses and doing things like that on the side. So a lot of fun. Now, before we get today in this presentation, I'm going to go ahead and turn this over to Mr. James McNay, and he's going to introduce himself. James, are you there?
I am here. Thanks, Ted. So as Ted said, my name is James McNay. I'm the Director of Consultancy and Engineering at Micropack Engineering. I've been involved in fire and gas detection designs for the last decade, and I'm involved in generating and developing a lot of the guidance in the marketplace with respect to fire and gas detection design. I'm also currently the Fire and Gas Chair for the Safety and Cybersecurity Division of the ISA. And similar to Ted, in the interest of showing that my life doesn't solely revolve around work and fire and gas detection, in the rare summer months we have here in Aberdeen, I enjoy heading out on my motorbike. And in the winter, I've recently taken up curling, which I've got quite involved in. It's become a little bit of an obsession for me. And an activity that's available all year round for me is watching the Scottish national football team perpetually fail to qualify for any major tournaments.
Hey, awesome. Hey, thank you so much, James. I appreciate that. And whenever I see this slide when you talk about curling in the winter, I always just think that you're just working out in the winter. But that's just me being me. No, I appreciate that, James. Thanks for sharing some of your hobbies. I think it's always fun to kind of learn a little bit more about people than just what we professionally do.
Yeah.
I'll go ahead. I'll jump into, we have a few intro slides here, and we're going to jump into the meat of today's conversation. If you don't know who we are, we're exida. We were founded in 1999 by some of the top reliability experts. The one point I want to get on this slide is that we are a global company. We have little red dots probably a little everywhere in the world. We actually have a few more we can add from this map. Our latest office that we just opened was in India. And whether it's functional safety, alarm management, cybersecurity, as I mentioned on the list of development standards that we're working on, we kind of do a little bit of everything now, and we're just constantly expanding. And the reason for that is because we stay involved with the complete supply chain of functional safety and many different industry sectors. I mean, we start off by helping the equipment manufacturers who actually produce products. They require this type of product certification, but what's unique is that we also get to help the end users who actually use those products. So we have that unique situation where, as we're working with the manufacturers, we kind of already know what their customers are going to need. And so it's kind of a win-win situation there. Now, we provide services in software tools, training, consulting, even in giving procedures related to functional safety, security, and reliability. And how we're able to achieve all of that is we kind of set up different silos of our business, whether it's in consulting, where we're going out there and just solely helping them, where they're not really achieving any type of certification. We'll work with the engineering tools. This is one area I learned quickly to love. I was one of the old-fashioned ones where I came and I wanted to do it all myself, but man, the tools are so nice. They save you so much time. Today we'll be talking about product certification and how to use a certified product. And then, of course, we have training, reference materials, and the personnel certification if you yourself wants to become a mentor or leader in the industry. Okay, so today's webinar, before I get started here, I want to make sure everybody understands that there is a question toolbar there for you. Please feel free to use that, ask as many questions as you would like. The first session that we had, we actually ran out of time. People asked too many questions. So I hope that happens again, because all the questions that you asked today, I'm gonna take with the morning session questions or the previous session questions, and I'll combine. James and I will make one big document, and we'll send it out to everybody, so everyone has every question and every answer to the questions that were asked on these webinars. But today's webinar, we will be focusing and discussing why so many end users are finding tremendous value in using these certified detectors. And we'll talk about what certification path is going to be best for you for the situation that you're in. And then, of course, we're also, after you do certify a product, the road doesn't end there. It actually becomes very critical on how you're going to use this product in the real world, and how important it is to put these detectors in certain places, and the reasons why you put them where you put them. And that's the portion that we wanted to pull one of the experts in fire and gas, James McNay, on today's webinar, because he is a true expert that can explain this in such a way that even I will understand it. So let's go ahead. We're going to jump into the product certification side, which is one of my fortes here. Now, before we talk about a value of anything, does everyone, well, obviously you can't talk because your mic is muted, but rhetorical question: does everyone understand what certification is and what it entails? Well, certification is a third-party authentication, basically done against a set of requirements. When we get audited every year, ANSI, who's the American National Standards Institute, they come back and say, look, you need to have a certain scheme when you're doing a certification. And so that's what we've developed. That's what we get accredited to. That's what we get audited to. And it's based off of your international standards, whether it's IEC 61508, IEC 61511, it could be the cybersecurity standard of IEC 62443. And what's important to know about certification programs is this: it's not just a product. It could be a system. It could be a component. It could be people. All these things are getting certified. So it's not just like what you would say, hey, there's a valve or there's a detector. No, it could be even an entire system of it. Functional safety certification also involves a detailed analysis of both your engineering process and design margins. Usually that results in that random failure rates, like an FMEDA, where you'll get a set of numbers in all your different failure modes, whether it's fail safe, fail dangerous, if it's detected or undetected. And nowadays, we're even starting to talk and implement cybersecurity into these certifications and start getting ahead of the curve, so that people are thinking about this earlier rather than later, when it's so much harder to implement something that's already been developed, right? I have a quick question here that I can answer right away, but for those who did not attend parts 1 and 2, they're asking if we can share the PowerPoint presentation. What I'll do one better. I'll make a note right now, and in my question and answer sheets that we're going to give out to everybody, I'll make sure I include links or descriptions as to where these webinars are and how you can get even the slides. So great question, and yes, we'll make sure we put that all together for you. Thank you for asking. Okay, so now that you briefly know about what certification is, now let's talk about if certification is even required. Because in short, no, certification is not required. So then you have to ask your question, because we get that a lot. Well, do I have to do this? Well, no, you don't have to do anything, really. Now, some places in the world are starting to make it a requirement, so I will have to say yes in those areas. But in the majority, no, you don't have to do certification. But why is there such an increasing demand by end users that are requiring the certification? And I kind of wanted to share with some of the things that we found by doing this for so long, because if they want to make a purchase, a lot of end users are actually starting to say, no, I want this product certified. And here's why. Because, there's things called a CapEx, right? When they say reduce CapEx, well, if you're not familiar with the financial terms, basically it means capital expenditures, right? And that's basically money that's spent by a business or like some type of organization who maybe they're acquiring fixed assets, maintaining fixed assets, or maybe they're buying more equipment, right? So if they're trying to buy detectors, or if you have a product certified, you know what you need right away, and so that can help reduce your capital expenditures. You then have operating expenses as well. What that is that's kind of your ongoing cost for running that product, right? So if a product's more reliable, guess what? You don't spend as much in operating expenses as well. So if you're using your equipment correctly, or if you know how to use it because it was a certified product, hey, guess what? You can actually reduce your spare part types because you're using it correctly. It's not failing as if you used it incorrectly, right? And then also many process industries, much like mining, oil and gas. Today we'll talk about fire and gas companies, but they're viewing IEC 61508 certification really as a measure of product quality design, or design quality, I should say, because a better design is what? It's going to be less risk and it's going to be less maintenance. And that's the name of the game. Nobody wants to buy something for it to just break. And then a complete IEC 61508 certification program, that's going to supply system designers with that valuable information that they need which is going to reduce their work by hundreds of hours. And why do I say that? It's because if say you have two products in your hand, one, it lets you know what your failure rates are going to be for safe, undetected, detected, if it's going to be a dangerous, undetected, right? So all those different failure modes, if you have a product and it already tells you all the answers as to what you need to develop your system, but then you have another product where you have to figure it out yourself, or maybe go the proven use route, you're going to be, I believe one person said they spent close to 600 hours trying to figure out these informations, these numbers. Whereas if they would have just spent a couple bucks more, they could have had a certified device. So you can see the value there as well. And then I know I briefly touched on it, but there are regulatory agencies that are starting to require products with IEC 61508 certification in safety application. And I guess the list can go on. And that's why I'm kind of saying, like, look, wouldn't it be nice if you were an end user, knowing what I just mentioned now, and you were able to use a product that was already so capable compared to a product that wasn't? That to me, that just it makes sense. And if I'll leave you. I feel like I'm jumping on a soapbox here, but I'll leave you with one last comment, because it's something I've always carried with me. It's that this is something my father always told me. He said, look, if you are an expert, and you're an expert, let's just say in plumbing, don't pretend to spend time on being this expert electrician. What he told me is he's like, surround yourself with experts in other areas, but don't just do that, use them, right? So have these people of these other professions, but use experts when you need them. Never pretend like you can do something that someone else spent years and years doing already. Why reinvent the wheel, right? Because we never get time back. And all that time that you spend really equates to money that you could have been doing other things. So he always said, don't pretend to be an expert, just find an expert. And if you love doing something, make it a hobby, but don't make it a profession. And that's why certification is one of those areas where having a certification, it will save you a tremendous amount of time, and it's a long-term benefit. All right, so now let's go through these certification processes, and then we'll pull James in, who will teach us how to use these products correctly and where to place the detectors and the advantages and disadvantages of them. So if you look in front of you, quickly, before we talk about the 3 paths, I just wanted to share one misnomer, is that people think when they get a product certified that the certifying body has to do everything. No, that's only if the manufacturer doesn't have any experts in their facility to do these tasks, because the only 4 things that exida really needs to do, or a certifying body, I should say, is the black boxes you see in front of you. There's the gap analysis, there's the architecture concept review, a safety case review, and then they issue the certificate. So for our certifying body, that's what we recommend as the mandatory items. The rest that you see in red, there's no reason why that manufacturer can't do those things. And so now what we'll do is we'll now talk about the different certification paths, right? Because there are 3 options available per our scheme that we get accredited to. The first one is the design and test process that's fully compliant. What that really is that's your new product. You just developed it. Maybe it's in development right now. You can still go through the process and it has no field history, right? So that's option 1. Option 2 is where you have a product. You want to make changes to it. It's been out there for a while. You can produce operating hours, so we can say, hey, it could be proven in use. And then the last one is it's one that's probably been around forever. It's never going to change. Maybe it's end of useful life, but you still got people that want this product. You can get that product certified to no changes allowed, which means there is no modification procedures. And that one you can usually get certified really quick because you don't have to meet a lot of the requirements of the standard, and that's also an option. So let's go through those 3 options. The first one, like I spoke about, it was that new product with no field history. The first thing you want to do is you want to have that new design must have that full hardware failure analysis. And what that is, that's your random failure integrity. The next step is your new design. It has to follow that design process requirements. What does that mean? We want to make sure that this new product, what did you do for testing? Where was your validation and verification? Do you have an SRS in place? Show me the specs that you thought, because we want to make sure that it was built correctly so that when it becomes a certified product, it goes in the industry and goes into the field, it must follow a certain procedure so that we can minimize any kind of risk. Right, and then that's what that is that's your systematic integrity, right? So now you're saying, okay, to reduce failures that are going to be systematic failures, make sure that you designed it correctly and you followed the procedures of IEC 61508, because it wasn't tested and trued yet. It's just a new product. We don't know if it's going to perform correctly. However, because you went through this process, we have a better assurance of it. And then the last thing that you'll see in all 3 of these options are that you will need a safety manual created to explain how to use this product, which makes sense. If we look at that chart that I showed you previously, the chart I showed you previously was really just the middle portion there. If you notice, there's 2 tables on the left and the right, one that says exit analysis reports, the right side says consultant client documentation. Those are the 2 that just got added in, and we put those there so that you could see what exit will do or the certifying body will do, and you'll see what the clients will need to produce, right? So for a new product, as you go through that process, they'll need to do a functional safety management plan. They'll need to develop an SRS, a validation test plan, and it goes on and on. And then once you get through, you meet all the requirements, you get your certificate. And that's for a new product. And I can go into much more detail on this. However, we do have other webinars that go into more detail for these different processes. And if that's something of interest to you, I can provide you links for all these. But for today's sake of time, I really want to get this webinar over to James because I do feel like his section is going to be very, very important for everybody on this call. The next process is option 2. This is the one where you have a product that's well defined, you have field history, you have shipment information, return information. Maybe you've had 100 products out there, so you have maybe 3 million for SIL 1, 30 million for SIL 2, or maybe 300 million for a SIL 3 application for proven in use. What's that saying is, look, I already have that full hardware failure analysis. That's the FMEDA that will perform for you. What changes now is that when you get to your systematic failure integrity for that product, you now don't have to do some of the design and the beginning testing stages. Why? Because you've already proven and shown from your failure and shipping information that it's a tried product and it works. You don't have any failures coming back. And the one thing that you'll have to show is you'll need to show that you have a procedure to make changes. So do you have a modification change procedure? How do you make a change? How far back in the life cycle do you go to make sure that you're catching those changes? Because sometimes you'll make a change thinking, okay, I fixed that problem, but that change actually messed something else up in your product and you didn't realize it. So we want to make sure that you go back far enough in the life cycle to iron out any other issues that may come from a different change, right? So option 2 is probably the most popular. It's the one that most people go for. Why? Because it gives you the flexibility. You don't have to run to a certifying body every single time you make a change anymore. You can make your own changes, and then when it comes up for renewal, you just tell the certifying body what you did. They'll review those changes, and you're off and going again. And it's a very nice process. And then, of course, we talked about the safety manual, teaching the end users how you use it in whatever environmental conditions, and if it needs any redundancy as well. So what is the architecture? All right, so if you look at the certification process for option 2, you'll notice in this case the red X's or the red no symbols are good things here because they're things that you don't have to worry about anymore. So you can see even tool justification, software module test plans, things like that you don't have to worry about anymore, but you will need to include your shipment information, your failure records, because we want to make sure that that product is a good, sound product. Option 3, this is the one where, hey, look, maybe you have a product that's going end of life, or maybe another thing is, hey, you have a product that you got to beat your competitor out to the market and you have to have it certified. Well, you can always go this route, which is basically saying that it's almost like an instant in time. It's, hey, to this revision, to this model exactly, I want this certified. I'm not going to make any changes. This is what I'm selling, and this is all I want, right? And so what you have to do is you still have to get that FMEDA done. Excuse me. You have to get that FMEDA done, which is step A. B, the thing that changes here, you can see that I crossed off the design process must meet requirements for ECNs. What does that mean? That means, look, you don't have to have a change procedure. You don't have to have a modification for change. If you do make a change, you're going to have to go back to the CB, right? Because all that's certified is that one instant, that one revision, that one model. And then, of course, you'll have that safety manual that's going to explain how to use that product. And here, look at all those red X's, or those red boxes there. Notice everything that you don't have to do. And that's why this process is so much quicker, is because there's a lot of things that you can avoid, you don't have to worry about. And so there are people that have chosen this route simply because, one, they want to go to time market, or two, maybe the opposite. They've been out there for so long, they just need to get it certified. Because why? End users are wanting these certifications more and more because it's less work for them. All right, so kind of to recap here, and then I'll jump this over to James. But so what is the value for manufacturers? Well, the first thing is you get that third-party review of the product. Who's the CB's main objective is to what? We want to find faults in the design, because what that does, it ultimately reduces it lowers the life cycle costs, which is what? It helps you with redesigning a product, because that can be so expensive. And so the sooner we can get in there, if we can see anything, if we find anything, you can make those changes sooner, right? The next thing is it does increase the marketing and the sales efforts. You now have something that's a step above your competitor if you get something certified. And of course, there are going to be increased costs initially, right? Because you have to pay money for a certification, but there is a lower risk with your product when it gets out in the field, right? You get less returns. You don't have to worry about rework. And there is a savings over the long period of time. For an end user, here you're going to have less spurious trips. Why? Because it's going to have it's going to help with unnecessary shutdowns, because you're going to be developing your system correctly. Maybe you have too much redundancy in your current system because you didn't know if it could have redundancy, if it needed redundancy. You do have that increased safety. You will get less failures in the field. Why? Because that end user is now using that product correctly. There's no guessing involved. They didn't have to do their own calculations. You come out with a more robust system. And of course, most importantly, you get that third-party review. And why I say that's so important is because every person that's selling you a product is going to tell you they're the best. And they're going to tell you, they're going to have 30 reasons why they're the best and why their competitors aren't the best. And here's a way for you to say, okay, look, this is a third party. They didn't have, they're completely impartial. You know, they judged it based off of numbers and analysis, and there's no emotion tied to it, right? So it's kind of nice, and end users usually appreciate that as well. So the next thing here is, sure, you get your product certified, and it's what I said at the beginning is it's really not the end of the road, because in fire and gas, not only should you make sure the product is used correctly, but even the placement of that detector is so critical. So at this point, what I'd like to do is, for further discussions on that placement, I'd like to pass this presentation over to one of the fire and gas industry experts, Mr. James McNay. I want to thank you again for your time on today's webinar, and I will go ahead and present it, change this presentation to you, and take the floor, sir. It's all yours.
All right, thank you very much, Ted. And just to echo Ted's thanks to everyone who's dialed into the webinar today. It's very much appreciated. The first thing we're going to do is I'm gonna give an overview of who Micropack are as an organisation, just very briefly. We're a hazard detection company. We've been involved in fire and gas detection since the 1980s as an organisation based in Aberdeen in the northeast of Scotland. We carried out the first fire and gas mapping review in 1989 in the Forties field in the North Sea. Although it wasn't referred to as fire and gas mapping at that point, that term essentially was coined in the early 1990s. Our core business is very much in consulting and software, the provision of fire and gas mapping software tools. The Micropack consultancy team design hundreds of fire and gas systems annually. And as I mentioned, we also provide our 3D fire and gas mapping software, which is commercially available, and provide fire and gas training should an organisation wish to take that expertise in-house. Micropack run the Micropack Exida Fire and Gas Detection Design and Technology FGP course, the Fire and Gas Practitioner course. Now, those areas of the core business are very much related to the consultancy, but we do have another arm of the business, which is the flame detection. So we pioneer in intelligent visual flame detection, but a lot of people don't realise that we actually also develop conventional flame detection, or some of the more traditional flame detection technologies as well, the likes of your triple IR flame detection, the radiant-based flame detection. So we essentially have two main strands of the business: flame detection and consultancy and engineering, and the software as well, obviously. Now, the content of today's webinar is very much going to focus on the consulting aspect, the determination of how many gas detectors do we want to position, and how do we decide where we want to place those detectors. So gas detection mapping and detector placement is one of the most complex aspects of fire and gas detection. By complex, we generally mean something which isn't well understood. It might not necessarily be complex, but if we don't understand it, it seems complex. There's multiple methodologies for different applications, which are all being applied in vastly different ways. And added into that mix is the claim that one methodology may be better than another methodology, which is usually dependent on what piece of software someone's trying to push perhaps at the time. The important thing is to appreciate that a methodology is very much suited to an application. There's no such thing as a perfect methodology when it comes to fire and gas detection mapping. This webinar is aiming to answer, the design aspect of this webinar is aiming to answer the questions of what detectors will respond to the hazard in question, where should I position my detectors, how many detectors do I need, and how can I be sure that the area of concern is protected to an acceptable level. Now, gas detection mapping, if it's applied in a reasonable manner, can help to achieve project certainty by providing that optimized detector coverage, which is verifiable. It can help to reduce design time. It can assist in design alterations and provide a fully documented audit trail of justifications of the design. It provides performance targets of the system, and all the assumptions and detector location information can all be stored within the gas detection mapping project. So what is gas mapping? Well, gas mapping is the holistic process of determining the detector placement through the application of both engineering knowledge of the detection technologies, the application and the performance requirements of the system, and also an adequate modelling tool, as well as that engineering knowledge. Now, you'll notice that engineering knowledge came first in this instance, and with any modelling tool, its purpose is to verify the design of an engineer. Now, the software tools shouldn't drive the engineer, but this has been somewhat lost when it comes to fire and gas detection design. There's been a real drive towards how important the software aspect of the design is. So we feel it's quite important to bring this background to fall more in line with other engineering disciplines, where the engineer still designs the system and the software verifies any assumptions that are made in that process. Now, with respect to the process, the engineer would typically review the hazards, the escalation potential, performance definition, mitigating actions, and so on and so forth. The modelling tool of choice would then be used to apply detection thresholds, detector positions, the detector voting of the system, which then provides the detection coverage and the contributions. Again, the engineer then reviews those coverage factors and takes a decision on the adequacy of the layout of detectors and logs those results. Now, whether your site methodology would use a traditional linear risk assessment, like a cause and effect style analysis, or whether a more modern systems-based risk analysis is carried out, fire and gas detection is ultimately classed as a safety barrier. In light of that, this slide here shows where the focus of gas detection is placed, just to the right of the incident, which in this case is a break in containment. So the gas has been released into an area. As we're designing a gas detection system, rather than a gas sampling system, we're concerned with the gas accumulations which might result in a deflagration. And a common performance requirement for gas detection is to prevent an explosion over pressure of 150 millibar or greater. That's commonly associated with pressure-induced damage. From that, it's quite clear that we don't want to design to detect small leaks as, well, first of all, it's virtually impossible, and it's not a particularly risk-based approach. What we want to design is to detect various gas dispersions that will likely result in the placement of detectors in locations where the gas accumulation may actually present the risk. The accumulation of gas rather than just where the gas may go. So this brings us to the application of performance targets. So in order to verify detection performance, we require a yardstick against which we can measure the coverage. How we determine that yardstick is the escalation potential of any given process or facility. And the easiest way to articulate this is to ask whether we would want the same detection layout in an open onshore process area where personnel can run away or the processes themselves can be easily separated. And we compare this to an offshore congested area where a gas accumulation would occur in a confined space. Ultimately, these differences will determine the ignition potential and the escalation of that ignition, which will later form the target that we want our gas detectors to meet. So with these performance targets being fundamental to the resultant number of detectors which are required, we define the performance targets as a formal statement of how you want the gas detectors to perform. In order to do this, though, we do require a methodology from which to define that target. Now, this methodology can stem from an end user's own guidance or philosophy on how to design gas detection, or it can come from a national body with a standard or a regulation, although they are not particularly common. So there's usually a gap there with respect to what the overarching methodology should be. So where those gaps exist, it's important to iron out in the early stages what the intention of the gas detection system is, so that all parties are clear on what the philosophy behind detection should be. So there's a bit of an ongoing debate in the industry about where and when to apply dispersion modelling to the gas detection design, where we would be predicting where the gas can go. Unfortunately, there's a lot of contradictory and often misleading information out there with respect to this. It can be difficult to know what methods are applicable and ultimately what design method would present the optimized layout. When deciding a way forward with respect to gas detection design, we have to consider what the intention of the design is. Our gas detectors are installed to mitigate the consequences of a release of gas. Now, the Health and Safety Executive in the UK, their research into the subject discusses that the systems are there to prevent explosion overpressures above a specified threshold. It's therefore safe to say that our design should focus around ensuring that a certain volume of gas, which would present that gas explosion overpressure, doesn't occur without being detected by a device. And that's where the target gas cloud methodology comes from. It sets the volume of gas of concern as the performance target and guides the designer to position the detectors so that that specific accumulation doesn't remain undetected. And from the images that we see on this slide, we can see that as the congestion increases, the flame front speed through that area will also accelerate. So the higher the congestion and the confinement, the smaller a gas cloud we require to prevent quite a nasty ignition and a nasty explosion. And it's particularly clear on the slide on the right-hand side there, when we see the comparison of an area with 78 pipes compared to an area which has 42 pipes. And certainly after 60 and 90 milliseconds after ignition, you can see the difference in those explosions. The one on the left obviously being far more severe. So this approach of ensuring gas clouds of concern are not undetected doesn't fit well with a method which attempts to detect based on probabilistic gas dispersion. These methodologies often allow detectors to be removed if the gas doesn't travel in that direction in enough of the dispersion scenarios. Now, the approach doesn't account for the fact that those scenarios may result in the highest consequence with respect to accumulation of gas. When we consider risk approaches like, for example, as low as reasonably practicable, it's fair to say that if a gas detector only detects gas in 1% of release scenarios, it could be removed. But this would be a difficult justification in court, for example, which would use the so far as reasonably practicable model, which is a far more precautionary approach, and generally would say that if a barrier can be placed and wasn't placed, that's a very difficult position to defend. And in the event that there is an explosion, for example, with multiple fatalities, someone could argue that, okay, we removed detection because it was only operational in 1% of our dispersion models, so the problem was unlikely. But a prosecution lawyer would rightly say, what do you mean it was unlikely? There's been multiple fatalities. So this is particularly compelling when we consider the alternative method, which would ensure that a gas cloud of concern would be detected 100% of the time, notwithstanding all the discussion that obviously Ted had at the start of this presentation about how reliable our gas detectors are and how reliable the mitigation functions would be. So the most important point here when we talk about probabilistic gas dispersion is sample size. How many scenarios would we need to run before a designer could feel confident in her results? If we consider even a small process area with the number of leak locations across multiple elevations, the number of horizontal and vertical orientations of the leak, the countless environmental conditions which would affect the release, there are literally millions of leak scenarios to consider. So let's have a look at some of our simulation models. Using a CFD tool, using computational fluid dynamics, you're unlikely to be able to run more than 50 simulations. And even that is quite unrealistic if the project is to come in on budget and on time. On the other end of the scale, we have the sort of more basic two-dimensional models which celebrate being able to run tens of thousands of simulations. Now, that's great. You've now got almost up to 1% of the possible scenarios which could occur. And there's a huge number of assumptions built into those models. For example, some of those models wouldn't consider near-field blockage. There's few scientific studies which would accept a sample size of less than 1% to have a reliable outcome. And I often compare this to taking a cup of water out of the Gulf of Mexico and concluding that there are no fish in the Gulf of Mexico based on your sample. But in a time of cost cutting and optimizing as far as possible, does that mean that gas dispersion designs would reduce my detector count? That could start to make them more attractive despite those limitations. Now, this actually brings us to another misconception, that using the target gas cloud approach rather than the dispersion approach will result in more detectors or would be less effective in some way. So this webinar is going to aim to debunk some of those common myths around that topic. So we'll start by looking at some of the regularly cited statements on gas detector effectiveness. Now, the UK Health and Safety Executive statistics show that around about half of the gas releases in the North Sea in the oil and gas industry were undetected over a 20-year time period. This has led to a narrative being drawn which is not necessarily based on factual analysis. The narrative states that gas detector placement is inadequate and the methods on gas detection placement are inadequate. What's not considered in that analysis is whether the gas releases were large enough to the point that the gas detectors would be expected to respond. And that's with respect to accumulation, not the size of the release itself. It doesn't review that the layout of the detectors was even in compliance with the method which was expected to be employed. And also, were all the gas detectors even operational at the time of the release? Now, with the number of gas releases, it would be difficult to gather all of that information, but we should be a little more hesitant about drawing fundamental conclusions based on that sample, with that limited data. So, as discussed, there's also a narrative that scenario-based modelling is going to reduce the number of detectors required across the board. However, much of the data to back up this point is flawed in its assumptions, now, which aren't always made clear. Now, the graph on this slide is often cited to show that when using a scenario-based approach, the effectiveness of the detector you place rises quite rapidly as you then add more detectors, but then tails off eventually, with the assumption that there will be a point at which adding more detectors becomes less fruitful. Now, this is true, but only when validated against the same simulations used to place the devices in the first place. It compares this approach to the target gas cloud approach, where the effectiveness of the detectors placed is less pronounced and tails off even quicker. When reviewing the y-axis and seeing that the geographic approach is being measured against the leak scenarios being detected, it actually starts to show why we've maybe got a flawed appreciation for the effectiveness of the approach. If we were to flip this round and check the effectiveness of the leak scenario approach by checking how many dangerous gas clouds are undetected, you would verify that the geographic approach is 100% effective and the scenario-based method is not. So, as also stated on this slide, we don't really care if we detect 99% of the leaks, if the 1% that we don't detect is the one that would actually cause an explosion with an overpressure of concern. So ultimately, all of this must mean that the geographic approach must result in more detectors than the scenario approach, except that's not true either. At Micropack, we've reviewed many scenario-based layouts against geographic layouts, and we're yet to find one where the geographic layout cannot be more effective with fewer detectors. This is not to say that one doesn't exist, just that in reality, we're yet to find one. As most of these examples I've reviewed are confidential, I will need to use an example which is in the public domain and is actually used as a selling tool for the scenario-based approach to demonstrate my point. So the number of detectors in a scenario-based assessment will be primarily dependent on the number of scenarios that the designer decides to run. It's worth noting at this point that no overarching framework or international standard or guidance exists which can be used to determine how many scenarios are adequate. This opens up the significant potential that two identical areas with identical risks and processes will have wildly different gas detection layouts. A nightmare for change management and auditing, I'm sure anyone in those industries could appreciate. If we run only one scenario and place the detectors where the gas goes, this will result in hardly any detectors, and they'll detect 100% of the gas release scenarios modelled. Now that's an extreme case, but does show some of the problems associated with this form of assessment, in particular for external applications. Now, no engineer would class that as a representative sample, but I have seen designs which would rely on between 10 and 20 computational fluid dynamics scenarios and place detectors based on this. This is with no appreciation given to whether the gas cloud migration to that location actually presents the root problem the gas detectors are intended to mitigate, which is explosion overpressures. So even scenarios where tens of thousands of releases are modelled with some fairly significant assumptions built in, surely can't be classed as adequate. As previously mentioned, this is still less than 1% of the potential scenarios which could occur, and generally won't account for factors, as I said, like near field blockage, which impact on practically every gas release in a process area. So ultimately, if we run what would credibly be classed as a suitable number of scenarios, we generally find that gas goes everywhere. So we'd have to place our detectors all over the module, whether an explosion hazard exists in that location or not. This surely can't be classed as an optimized layout. And as mentioned before, it's based purely on how many scenarios that detector detected that gas release and how many scenarios were run, not how severe that scenario actually would be from the point of view of an explosion overpressure. This has been seen regularly, resulting in quite a significant number of detectors, and is also quite an expensive way to conduct the analysis. These simulations can be very expensive. So essentially, the public comparison here between scenario and geographic approach show the benefits of a scenario approach of a dispersion analysis compared to a volumetric analysis. But a lot of the assumptions here are quite flawed. This specific example shows that a scenario approach managed to reduce the number of point detectors from 27 down to 17. Why does it only use point detectors? Well, perhaps because this helps to paint a picture. In reality, no geographic-based design would rely on such a prescriptive grid of point gas detectors. And when we actually critique and review the volume, it actually becomes clear that even 17 detectors in this area is massively over-engineered. In fact, a true volumetric approach would easily reduce the number of detectors required here. If we assume that the yellow circles are 5 meters in diameter, based on obviously the highly misunderstood 5 meter spacing concept, showing that a 5 meter cloud in this area presents the explosion overpressure of concern, we could quite easily run 5 line of sight detectors through this volume. This would reduce the number of detectors from 17 down to 5. Now, not only does it optimize the number of detectors, but also guarantees that that target gas cloud of concern can't exist anywhere within that module without activating a detector. If we verify the scenario-based approach from that point of view of where can the gas cloud, which would result in an unacceptable explosion overpressure, exist, we find that there are in fact many locations that cloud could remain undetected and present a hazard. So you can summarize this as an over-engineered system which still leaves gaps in achieving the functional requirement of the installed system. Now, while it's true that this is one example and not representative of all examples, it is an example which has been generated to promote the scenario-based approach. And if it's that easy to debunk a tailored example, it doesn't bode well for the widespread application of such an approach. Now, moving away from the methodology aspects of optimized design, detection technology, as with flame detection, is critical in making sure that we don't over-engineer the system. The technology also needs to be deployed in adequate locations to allow for maintenance accessibility, and also in such a manner that it will allow adequate operation of the devices themselves. So should open path gas detectors be used, for example, a clear line of sight has to be required to make sure that the receiver can receive the signal from the transmitter. The gases intended to be detected have to also be reviewed to ensure that the technology applied will be appropriate in detecting that gas, along with calibration requirements to ensure that we don't underread a potential gas release whenever there's potentially mixed streams, for example, in the process. Set points of the devices should also be considered with the voting logic, as these kind of decisions are going to impact on the resulting coverage and the suitability of the system. If executive action requires 2 alarms on the high gas alarm set point, then this will result in a poorer target gas cloud coverage compared to executive actions on 2 low gas alarms, for example, with the low gas cloud diameter being much larger. But this can give rise to a higher degree of false alarm potential if you lower that set point. So it brings us back to the selection of the technology based on the environment, which is just as critical as the modelling portion of such a review. And finally, how that technology operates must also be accurately covered in that modelling tool. If we're using, for example, an open path gas detector, those devices don't simply rely on gas touching the beam to provide an alarm. The coverage of these devices shouldn't just be shown as a basic sausage of coverage, for example. The coverage like this is misleading with how those detectors actually operate. Open path gas detectors will require a certain concentration of gas across a given length of the beam in order to activate that device. And it's quite important this is accounted for so that the designer can actually make an adequate decision on whether that layout is adequate or otherwise. So on this slide here, we're just showing a couple of examples of what gas detection mapping can look like. Now, this is obviously a very basic example here of our test facility at Micropack's office. But generally, we bring in the 3D model with the geometry playing such a large role in where we can place detection and the effect it will have on the detector coverage. We then have to grade the volume based on our escalation potential. So what kind of gases do we want to look for in the area? We then place any existing detectors that may be in the area, and then we can run our coverage assessment. And we can see an example here of a very basic and stripped down offshore process area. We use this model in our training course. It's very easy to navigate, but I'm sure everyone will agree that it's not really representative of what an offshore process module actually looks like. But what it does show is that you can actually have multiple gas grades even within one volume. So on the left-hand side there, you can see that we've got a congested region with a bit more equipment, with the red graded volume, which is looking for a smaller target gas cloud because that area is congested, and therefore a smaller gas cloud will result in explosion overpressures with the amount of pressure pushing back on that flame front. The orange area represents a more open-based area, so the target gas cloud of concern can be relaxed and is a little bit larger. Therefore, we can optimize that system throughout that process area. And we've got a few examples here of some assessments, just showing you that three-dimensional coverage. Very basically, to summarize this, the green volume you can see is where we achieve 2 out of n, executive action coverage. So 2 gas detectors are being activated by the target gas cloud of concern. And the orange areas are the areas where we've got 1 out of n coverage. So the target gas cloud that we're concerned about would only intersect with 1 device. And we can obviously get the percentage coverage as output from the software to help the designer. Sometimes looking at the 3D volume can be a little bit tricky if it's quite a congested area. So obviously you want to be able to look at these coverages from a 2-dimensional standpoint as well. And we've simply for this presentation, we've taken 3 slices at 3 different elevations to give a representation of that coverage. And quite importantly, we also have the detector contributions. Now, these are important during design because they can help the engineer to decide where best to place detectors, where our detectors will perform well and detect the gas clouds of concern, and where they're performing perhaps not so well, and then we can relocate that device or remove it entirely and optimize the system. Another useful use for the detector contributions would be in maintenance. So if you're operating a plant with 30 gas detectors and 3 of them are in fault, you can look at the detector contributions and make a much better decision on which detector to prioritize. So if you've got a detector and you've just lost 30% coverage of a volume, that becomes an important detector to bring back online. So essentially what this constitutes in is a requirement for both reliability and design through mapping which would include both engineering judgment and the modeling portions, and also an appreciation for the reliability of the devices to make sure that if gas does reach the device, we can trust that it will actually act appropriately and respond how we intend it to respond. All these factors come together to form obviously what's referred to as fire and gas mapping, the combination of fire and gas engineering and fire and gas modeling tools. So at this point, I'm going to hand back to Ted and thank everyone for dialing in once again. Hopefully it's been informative to you. And I think we've got a little bit of time for some questions, although I may have overrun ever so slightly. So back to you, Ted.
Hey James, thank you so much. I really appreciate that. That's some great information there. And yeah, you're absolutely right though. We do have a handful of questions here, so we'll get through most of them. If we can't get to some of them, we do apologize, but we will be running over a little bit. If you guys don't mind hanging in there 5 minutes after the hour, then we'll continue with these questions. But the first one here we have. Pretty basic one here, but just to clarify, somebody asked what the ECN number was, or ECN abbreviation was from the modification slide when we were talking about certification process. And that one, you're absolutely right. It was the engineering change notice. So that is what ECN meant, just so that you know that. Just a quick one there. Okay, so James, you have the next question here. Then let me just put to a slide where people can get some information. I'd like to just go to this one here so they have your contact information if they needed to jump off. But the question I have here is what percentage coverage is typically applied as a minimum requirement?
Yeah, that's a good question. And the answer is that there isn't really a set answer. It always comes down to engineering judgment. Unless the operator or end user has a specific requirement. Now, a couple of the end users in oil and gas do have requirements with respect to gas detection coverage. A common one is, 95% of the volume covered for a single device for alarm only, and then a second device to give executive action through 90% of the volume. Other operators have seen 80% specified, 80% coverage for gas detection. And the one exception would be where spacing is applied. So there's another methodology that I didn't really touch on tonight, or this afternoon, depending on where you are in the world, which is the spacing requirement. We often hear 5 meter spacing referenced. Now, in an example like that, technically you have to hit 100% coverage. Otherwise, you haven't met the prescriptive spacing requirement. You either have a detector at that spacing or you don't. The reality is, though, that generally you would accept a little bit of leeway. You would expect, if you get 95% coverage through a 7 meter spacing design, an engineer would look at that, see where the gap is, and take a view on whether it's adequate or not. So each individual area very much has to be taken at its own merit. And if it's a little bit borderline, there's no harm in opening it up to a group to all discuss and decide whether that coverage is adequate or not.
Awesome. Hey, thank you so much for that answer, James. I hope that answers their question, which it sounded like it did. Let's move on to the next one here. Can the software account for the LEL meter set point of beam detectors in the calculation of coverage? James, I'd let you have that one as well.
Okay, yeah, sure. Yes, it can. That's a good question. So I touched on the fact during the presentation that an open path gas detector doesn't operate the same way that a point gas detector would. It's very easy to represent the coverage of a point gas detector because it's giving you a percentage LEL reading at that point, at that position. An open path gas detector could be up to and beyond 120 meters in length. And if you get gas along that beam, you don't actually know specifically where that gas is. So, which is obviously why we use lower explosive limit meters, LEL meters. And the software does a calculation within the tool, what we call the beam attenuation model, which automatically calculates out the concentration of the gas across the distance of the beam so that we can provide as accurate as possible outputs in the assessment.
And it looks like this may be a piggyback question to what you just answered, because I know you just talked about point or open path detectors. And regardless of whichever one is better, is there any guidance or any guidelines on what type of detector to use in certain applications?
Yeah, that does tie in. There's not, essentially you have to look at a few different factors. You would have to look at the congestion in the area, because if we just look at it on the most basic level of point versus open path, if you don't have a clear line of sight, then you can't use an open path. But even within those technologies, we do have different types of that technology. So within a point gas detector, for example, it could be infrared based, all with varying different calibrations. It could be electrochemical, it could be a semiconductor device, it could be both wired or wireless. It could be a wireless point gas detector with the benefits that would come from that. So you essentially have to look at the application, the congestion, and also what kind of gas are you looking for. Even the age of the facility, what kind of budget you've got can determine what the best gas detector is for that specific application.
Perfect. All right, thank you for that. James, you're popular. I got another one here for you. Maybe somebody will ask a certification question. Come on, guys and gals. Can the mapping software deal with other specialized gas hazards such as H2S?
Yeah, so this is This is certainly common in some parts of the world where hydrogen sulfide specifically is a big problem, but other toxic gases are applicable as well. Now, the software can model that, but the method of design is different from what we've covered in the webinar today. So today we're very much focused on flammable gas detection accumulations. When you're looking at toxic, it's entirely about personnel protection. So where you place those detectors does change. You want to start focusing in on where people could be present. You want to start focusing on placing the detectors in the breathing zone, for example, at entrances and exits to various modules and areas where people could be walking, and the emergency exits and escape routes as well. So the model can be tweaked, it can be used to model that, but the grades look slightly different. It's a little bit of a different approach.
Excellent. Hey, thank you so much. All right, so we have two last questions here. If you guys have more questions, we'll have to hold them, or just keep asking questions anyways, and then we can get to them after the fact. But I just do want to be sensitive to people's time here. I know it's pretty late for you, James, where you are, but the last two questions, one, I do have a question, so that's good for me, and then one for you again, James, but I'll go ahead and answer this one. The question is, if we need a product certified quickly, can we do option 3 from your presentation, which was proven in use, no changes, or do we go for option 2? And can we go for option 2, which is proven in use with changes at a later time? Great. No, I like that question a lot, because this is something that people do ask for. And so my short answer is yes, you can. So if you have something that you're time sensitive, you need to get it out there, maybe you wait a little bit, because you know certification can take anywhere between 3 and 6 months long. If you want to get something out there quicker and you would like to go proven use with no changes, you can do so. And then as soon as you get your product certified, you don't need to wait. You can actually start working on with changes, which basically means we'd open up and let you know all the different requirements needed to have a certification with changes. And you can perform that. And then whenever you finish doing those things, you can then change your certificate, change the new expiration date on that certificate, and move forward. Yeah, it's probably a little bit more money because you're going to have to do 2 different processes. However, if time to market is very important to you, that's absolutely something you can do. You can do an instance time, that certain product at that moment, you can get that certified. And then if you want to make changes, we can let you know and help and assist you as to what you need to do to get a proven use with changes, which is the most useful to a manufacturer. So that's a great question, and I hope that answered your question there. All right, James, I'm coming back to you one last time. The last question of this webinar is, do users typically use the detector contribution tables or just go with the graphical coverage map?
I can certainly speak from within, from a design point of view within Micropack. You would definitely use a combination of both. When you first run a few scenarios, a few example assessments, you're looking at the 3D model for coverage and making some tweaks and just getting that to the point where it looks like your coverage is going to be suitable. What the detector contributions help you with is getting into the detail. So you can look at the 3D model and the coverage can look very nice and you can have a high percentage. When you look at the detector contributions, you can actually start to pick out that, oh, there's a detector in there that's only monitoring, 2% of the volume. Can we reposition this to a better area where it's going to increase our overall percentage coverage? So that's certainly useful from our point of view in the design to use both. What we hear from our users in the field, though, certainly the end users, the operators, is that the detector contributions are very useful during operation and maintenance optimization. So if anyone that's looked after a large facility with a high number of detectors will know that very rarely do you have 100% uptime where every detector is operating. So what is useful is deciding, you've got 5 detectors that I need to bring back online. Which one am I going to bring online first? You've got a limited number of maintenance engineers, and when you get that slot, the detector contributions can definitely help in deciding which one you go after first.
And there you have it. Excellent job, James. Hey, James, I do want to personally thank you for doing this series of webinars with us here at Exida. We always appreciate your time. We know that when we do these webinars, probably aren't the best times for you and your colleagues, but once again, we always appreciate an expert when we can get one on here.
No, you're very welcome, Ted. And I've got a 12-year-old Highland Park waiting for me, so I'm more than happy to do it up to this time.
Fantastic. Well, thanks again, everybody. This does conclude today's webinar. Thank you for everyone hanging in there. We went a little bit afterwards, after the hour, but we hope you found it valuable. If you have more questions, let me just throw up our contact information one last time. There you go. And please feel free to ask us questions. We'll get them on that spreadsheet. We'll send them out to you. And thanks again, everyone. We appreciate it. Take care. Bye-bye for now.